There's a particular kind of quiet that happens late at night when you stop doing things. Not the absence of sound exactly, the fridge still clicks, something settles in the walls, but a different quality of attention, the kind where you notice your own breathing, where small things become briefly interesting again. If you had a candle burning right now, you could watch this. You wouldn't need to know any physics. You wouldn't need to know anything, really. Just watch it. The wax at the base of the flame goes soft, then liquid, then it's just gone, and what was solid and white and faintly waxy smelling a few minutes ago is now, what? Smoke a little, heat mostly, light for a moment. The flame leans slightly to one side if there's any movement in the air at all, even the slow drift from a doorway across the room. It's a fussy thing, a candle flame, sensitive to almost nothing. But here's the part that took humanity an embarrassingly long time to work out. Nothing that candle does actually disappears, not one part of it. The wax doesn't vanish, the heat doesn't end. Every bit of warmth that moves from the flame into the air, into the walls, into the fabric of the couch you're lying on, it's still there, changed shape completely, moved into everything around it. But there. That's the whole idea, really. That's what this is about. It sounds almost too simple, and I think, I've thought about this more than is probably reasonable, that the simplicity is exactly why it took so long to see clearly. For most of human history, things just seem to stop. You push something and it slows down. Fire burns and the wood is gone. A warm stone left outside goes cold by morning. The most honest reading of ordinary experiences, energy runs out. Things wind down. The world uses itself up, which is wrong, beautifully, completely wrong. The stone isn't colder because the warmth disappeared. It's colder because the warmth moved out into the air, into the ground it was resting on, into everything touching it. Spread so thin by morning that no single part of the world is noticeably warmer. But the warmth is out there, diluted past the point of usefulness maybe, gone from the stone certainly. Destroyed? No, there's a difference between gone from here and gone. That distinction is, in some sense, all of thermodynamics. A candle burning in a room, if you could somehow account for every molecule the flame touched, every photon it released, every tiny pressure wave from the sound of it guttering, all of that energy would add up to exactly what the wax contained before you lit the match. Not approximately, not close enough, exactly. This is not intuitive. The room doesn't feel like a storage system, it just feels like a room. The wax itself is where to start, actually. Before the flame, before the match, before anything, wax is just sitting there holding energy it doesn't appear to have. Chemical energy, which sounds technical but is really just, the atoms in the wax are arranged in a way that has potential. Like water at the top of a slope, except molecular and invisible, and doing nothing whatsoever until heat is applied. Strike a match, touch it to the wick heats up, which heats the wax near it, which melts, which gets drawn up the wick by capillary reaction, which is one of those small, stubborn physics facts that still seems slightly improbable even after you understand it. And at the top of the wick, the liquid wax vaporizes, and those vapors ignite. That's the flame. It's not the wick burning, not the solid wax. It's wax vapor, combusting continuously, sustained by the heat of its own reaction, pulling up more wax from below. The flame is a process, not a thing, which matters because it means every moment of a candle burning is the flame remaking itself, using what it made last moment to make the next moment. It's almost, not quite, but almost, a loop. What's happening chemically is the carbon and hydrogen in the wax are combining with oxygen from the air, and that rearrangement releases energy. The bonds in the new molecules, water vapor, carbon dioxide, are lower energy than the bonds in the wax. That difference, that step down, is where the heat and light come from. The wax becomes gas, the gas becomes heat, the heat becomes the room. And the room this is where it gets strange, slightly, measurably, genuinely warmer. Not by much, not by anything you'd feel probably from a single candle over a few minutes. But if you had the instrument sensitive enough, you'd find it. The air temperature up near the ceiling a fraction higher. The walls absorbing infrared, the flame radiated outward. Your skin, if you're close enough, picking up warmth your nervous system registers as comfort or proximity. All of that, every degree of temperature rise in every cubic centimetre of air, is the candle, still the candle, just redistributed past recognition. I find this, and this is a personal thing maybe, almost more strange than the physics itself, that the candle is still in the room after it's burned. Not as light anymore, not as heat you can feel, but as the slightly elevated temperature of everything around you that will take hours to fully dissipate into the walls and then into the outside air and then into, well, it goes a long way eventually, but it doesn't stop. Is that remarkable? I'm not sure remarkable is the right word. It's more than that and also strangely ordinary. Something closer to load-bearing. The kind of fact that everything else rests on without ceremony. The person who made this undeniable, not discovered it exactly, but demonstrated it so carefully that no one could argue anymore, was a Lancashire brewer named James Joule, who kept meticulous temperature records, who had a slight obsession with measuring things that other scientists found gauche. He measured the temperature of water at the top of a waterfall and again at the bottom, and he found it slightly warmer below, by exactly the amount you'd expect if the falling water's motion had converted to heat on impact. Slightly warmer. The waterfall's motion now in the water. He did this on his honeymoon apparently, brought a thermometer to his own honeymoon to measure a waterfall. His wife's reported reaction to this is not in the historical record, which is perhaps its own kind of data, but Joule was right. The waterfall proved it. The paddle wheel experiments he ran in his brewery proved it again, stirring water with a mechanical paddle measuring how much the water warmed based on how hard he stirred. Motion into heat, every time, always the same ratio, nothing extra gone, nothing unaccounted for. What he was finding patiently, obsessively in a brewery in Salford was conservation of energy. Before anyone had fully named it, before it was a law. He was just measuring things and noticing that the numbers didn't lie. Back to your candle, or the imaginary one if you don't have one lit. The wax is gone. The room is slightly warmer. The flame, if it's still burning, is pulling up the last of the liquid from the base, and the pool is getting shallow now, and at some point, soon, the wick will be too short, the wax too thin, and the flame will flutter, shrink, and go out. Not because the energy ran out, because the system, the wax, the wick, the specific geometry of a candle that makes the capillary action work, came apart. The process stopped. The energy didn't. That's a distinction worth their holding. For a moment, because the whole of this is built on it. A process can end, a machine can stop, a star can go cold, but the energy that was moving through those things, it didn't go out with the flame. It moved into the room, into the air, into the slow quiet everywhere that everything eventually becomes. The candle keeps going, just not as a candle anymore. If you want to help keep this kind of thing going, slow, unhurried, built without a team or a budget, just the work itself, there's a Patreon where you can do that. This is self-funded every video, and the people there are genuinely why it continues. Even a small amount makes the next one possible. There's a link in the description if that feels right. There are 12 of these, 12 chapters, 12 different angles on the same idea, that energy is never destroyed but only changes form. Some of what's coming is more abstract than a candle. Some of it is stranger. One chapter later is almost entirely a pendulum in a dark room. But the candle is a good place to start. It's visible. It's slow enough to watch. It turns one thing into another, so plainly you can feel it on your face. What happens when that conversion goes deeper, when it's not wax to heat but matter itself to energy, is where we're heading. The room is already slightly warmer. That part has already happened. There is a particular kind of knowledge that exists before language gets to it. Not intuition exactly, not instinct. Something more like the understanding that accumulates in hands and eyes before the mind has organised it into a sentence. The kind of knowing that happens when you've watched something long enough that you stop being surprised by it, even though you couldn't explain under any pressure why it works the way it does. People had this about energy for a very long time, thousands of years probably. They just didn't call it that. They didn't call it anything. It was simply the way the world behaved, and you learned to read it the way you learned to read weather, not from a book, from watching. Water falling moves things. That was known. Not in the way a physicist would state it now, with the careful language of potential converted to kinetic, with the numbers that say how far and how fast and how much force per unit area. None of that. Just water from a height, directed right, turns a wheel. The wheel turns a millstone. The millstone grinds grain. This sequence was in use in ancient Greece, in Rome, along river valleys in Persia and China, for centuries before anyone thought to ask what precisely was being transferred from the water to the stone. The water fell. The stone turned. The bread was made. And the water at the bottom of the wheel wasn't qualitatively different from the water at the top. It was still water, still wet, still cold in winter, still the same river. But something had left it. Something had moved from the falling water into the turning axle, and then into the grinding stone, and then into the meal. Something had passed through. No one had a word for it. The miller didn't need one. Fire was stranger, because fire seemed like pure loss. Wood burns, and becomes ash and smoke and heat, and the ash is so obviously less than the wood that the arithmetic of it seemed to point in only one direction. Burning destroys. This is not an unreasonable conclusion. It is, in fact, the correct conclusion to draw from the evidence available to the naked eye over the course of a human lifetime spent watching fires. Things go in, less comes out. What comes out is messier, somehow, smaller, less useful. The heat itself wasn't being tracked. The smoke that carries off carbon, the water vapour, the invisible dispersal of everything the wood was, none of that was in the ledger, because you can't see where warmth goes when it leaves a room. You can feel it leaving gradually in the way the air gets heavier and cooler as the night deepens, but that doesn't look like the warmth going somewhere. It just looks like the warmth ending, which is, to be clear, not what's happening, not even slightly, but it looks like it. And for a long time, looking was all anyone had. There was a theory, a genuinely held, a seriously argued, professionally defended scientific theory, that fire released a substance. A real physical substance contained within flammable materials that escaped during combustion. They called it phlogiston, which is one of those words that sounds like it was invented by someone who wanted the thing to sound more real than it was. Phlogiston-rich materials burned well. Phlogiston-poor materials didn't. When something burned completely, it had given off all its phlogiston. The theory held for about 100 years, not because scientists were foolish, because it worked, after a fashion, as an explanation for a large number of observations. It was wrong in a way that was useful, which is, well, science is full of that actually. Frameworks that explained enough to be kept and refined and only abandoned when the thing they couldn't explain became impossible to ignore. What they couldn't explain was the weight. When you burn a metal in air, magnesium say, or iron, the ash weighs more than what you started with. Not less, more, which means something was added during burning, not released. Phlogiston couldn't survive that observation. Antoine Lavoisier ran the experiments, measured carefully, and the theory quietly came apart. What was being added was oxygen. The metal was combining with it. The burning was a chemical union, not a release. And the heat and light were the energy freed by the formation of new, lower energy molecular bonds. Lavoisier didn't discover conservation of energy, not directly. He was working on conservation of mass, which is related, obviously, more related than anyone knew at the time, but not the same thing. What he did was clear away the wrong answer so the right question could be asked. That mattered. The wrong answer had occupied the room for a century. The right question, when it finally came, was something like, where does the capacity to do work go? Not mass, not a substance, not phlogiston or any other name thing, just the ability to cause change. When a hammer falls and drives a nail, something in the hammer's motion passes into the nail, and the wood and the slight warming of the metal at the impact point and the sound that moves outward through the air. All of it came from somewhere. The hand that lifted the hammer, the food that powered the hand, the sun that grew the food. The capacity to cause change moved through all of that, from one form to the next, without any of it appearing or disappearing, just transforming. The word energy, in this sense, in the physics sense, was first used by Thomas Young in 1807 in a lecture at the Royal Institution in London, which is a detail I find slightly odd to hold because the concept itself is so much older than any name for it, and yet the name mattered. Having a word for the thing meant you could point at it across different systems and say, that quantity there, the one you're tracking in the water, and the one you're tracking in the heat, and the one you're tracking in the moving weight, those are all the same quantity. Same thing, different outfit. Young used the word and it didn't immediately stick. He was describing what we would now call kinetic energy specifically, mv squared divided by 2. And the broader meaning took a few more decades to settle. Language is like that. The word arrives before the full idea is ready for it, or after, and the fit is awkward for a while. The 1840s were when the awkwardness resolved. Multiple people, different countries working on different problems, a German physician named Julius von Meyer, an English brewer you'll hear more about in the next chapter, a Danish engineer named Ludwig Kolding, arrived, more or less simultaneously, at the same conclusion, that heat and mechanical work were interchangeable, and that the exchange rate was fixed. You always got the same amount of heat from the same amount of work. Always. And that this ratio, this stubborn, constant ratio, implied something about the universe that had never quite been said aloud. Energy is conserved, not approximately, not on average, not in most cases, in every case, across every system, in every experiment anyone had ever run or would ever run. The total energy going in equaled the total energy coming out when you counted everything. When you counted the heat, the sound, the deformation, the warmth in the air. Air came to his version of this through blood. He was a ship's physician in the Dutch East Indies. This is not the kind of biographical detail that appears in most physics textbooks, which I think is a shame. And he noticed that sailors' venous blood looked different in the tropics than in colder climates. Brighter red, less deoxygenated. His interpretation, in a warm environment, the body burns less fuel to maintain temperature, and so the blood returning to the heart has surrendered less oxygen. The body's heat production and its mechanical work were, in his thinking, expressions of the same underlying process. He was doing thermodynamics while looking at blood on a ship in the Java Sea, decades before anyone had named the field. What none of these men had, what was genuinely missing until the 20th century, was any sense of why energy is conserved. Not just that it is, not just the evidence that it always is, but the actual reason, the structural reason, if there is one. The answer to, is this a rule the universe follows, or is it something deeper than a rule? That answer came from a mathematician named Emmy Noether in 1918, and it is, well, it belongs in a later chapter where it can sit properly, but the short version is, conservation of energy is not a fact about energy, it is a fact about time, about the symmetry of time, about what it means for the laws of physics to be the same today as they were yesterday. It is, in other words, not arbitrary. The millers who watch the wheel turn without asking why, the physicians looking at blood in tropical light, the brewers with their paddle wheels and their thermometers, they were all observing the same symmetry, without knowing that's what it was. There is something in that which I keep returning to and not quite resolving. Whether it's remarkable that humans found this truth so slowly, or remarkable that they found it at all, stumbling toward it through watermills and burning metals and very carefully weighed ash. Both, maybe. Both at once, which is a contradiction of a kind, but not the sort that bothers me. The night air through a cracked window smells like rain that hasn't arrived yet, which is its own kind of stored potential. Everything sitting in the particular heavy way that precedes a change. The candle from the last chapter has burned down by now, but the room is still, somewhere in its walls and its air, holding what the candle gave it. The accounting goes on without anyone keeping it. That's been true for longer than anyone has had a name for it. It will remain true past the last name, past the last word. Something in the friction, in the slowing and warming and transferring, is still, even now, waiting to be fully understood. Not because the physics is incomplete, but because understanding is a process, not an event. It moves the way heat moves through a wall, slowly, pervasively, into everything around it. What it finds in the next chapter is a man stirring water in a brewery and refusing to stop measuring until the numbers made sense. Imagine someone handing you a glass of water and saying, "This is slightly warmer than it was a moment ago because I stirred it." Not heated it, stirred it. You would probably nod politely and then privately wonder whether the person was entirely well. Because stirring water doesn't warm it. Stirring is just motion, circular motion in a glass. The water goes around and then it stops, and nothing is different. That is the reasonable, sensible, obviously correct understanding of stirring water that virtually every person who has ever stirred anything has arrived at independently, without effort, and without being wrong in any way that their daily life would ever reveal, except it does. Warm it, that is, by a tiny, stubborn, measurable amount. James Prescott Joule knew this before most people were willing to believe him, and he spent roughly 20 years of his life demonstrating it with increasing levels of precision, and one imagines increasing levels of personal frustration. He was a brewer, not a professor, not a fellow of any society initially, not credentialed in the way that made 19th century British science take you seriously. He ran his family's brewery in Salford, which is the sort of post-industrial English town that smells faintly of coal and damp brick even in summer. He had equipment, he had patience, and he had a genuinely unreasonable commitment to measuring things other people thought weren't worth measuring. The thing he was measuring fundamentally was this. When motion stops, where does it go? Not where does the object go, where does the motion go? The experiment he kept returning to, the one that ended up mattering most, was embarrassingly simple in concept. A container of water, a paddle wheel inside it, connected by a cord to a falling weight. The weight falls, the cord unspools, the paddle turns, churning the water. Then the weight is at the bottom, the paddle is still, and Joule measures the temperature of the water. Warmer every time, warmer by a small specific amount that depended precisely on how far the weight had fallen. This is not the kind of result that impresses people at a dinner party. There's no spectacle to it. No light, no dramatic reaction, no transformation you can point to. Just a container of water that is, and this is where I find something almost funny about the whole thing, 1 or 2 hundredths of a degree Fahrenheit warmer than it was before. He measured this, he cared about this. He redesigned his apparatus multiple times to get more precise readings, used a longer drop to get more temperature change, added more paddles. The thermometers he eventually used were calibrated to 1/200th of a degree, for water in a barrel in a brewery in Salford. What he was looking for, though he wouldn't have put it in these words because the vocabulary didn't fully exist yet, was the exchange rate, not whether motion could become heat. He was fairly convinced of that early on. What he wanted was the exact number. How much heat precisely for how much mechanical work? Was it consistent? Was it always the same conversion, regardless of the method, paddle wheel or falling weight or compressed air or electrical current? Or did different methods give you different amounts of heat per unit of effort, in which case the whole thing was messier and stranger than he hoped? It was always the same ratio, same number. It didn't matter how the motion was converted to past. You always got the same amount of heat per unit of work within the precision of his instruments, and as his instruments got better, the consistency held. The number he arrived at, what we now call the mechanical equivalent of heat, was accurate to within a fraction of a percent of the value measured with modern equipment, in a brewery, with weights and wooden paddles and a thermometer thin as a finger. Here is where the friction comes in, properly, I mean not just as a concept. Friction was the problem before Joule. Friction was why motion seemed to disappear. You push a crate across a floor, it slows down and stops, and the obvious conclusion, the one that seemed self-evident for centuries, was that the motion had simply been destroyed by the resistance. Used up, cancelled. This is what friction appeared to do. It was the thing that ate motion, the universe's drain, and Joule was, in effect, watching the drain and asking what was on the other side of it. What was on the other side was heat, always heat. The crate warms the floor slightly, and itself slightly as it slides. Not enough to notice, not enough to matter for any practical purpose involving a crate and a floor. But the heat is there, measurable in principle if you had instruments sensitive enough. The motion didn't vanish, it changed. Friction doesn't destroy motion, it converts it. That sentence took an embarrassingly long time to become accepted fact, and I think this is a personal reading and it might be wrong. The delay wasn't really about evidence. Joule had evidence. He kept producing evidence, better and better evidence, across 2 decades. The delay was about categories, about the deep human preference for keeping things in their proper boxes, and motion was in one box, and heat was in another, and the idea that they were the same kind of thing, that you could trade one for the other at a fixed rate the way you'd trade currencies, required dismantling a conceptual wall that felt to many scientists of the time entirely load-bearing. William Thomson, who later became Lord Kelvin, who was extremely distinguished and extremely certain about most things, took years to come around. He eventually did. He became one of the strongest advocates of energy conservation as a principle, but he had to be moved there slowly, which I find oddly comforting, because it suggests that even very good minds sometimes need the evidence to accumulate past a certain critical weight before the wall comes down. The broader principle that Joule's work helped establish, conservation of energy, the first law of thermodynamics, says that in a closed system, the total energy doesn't change, ever. It moves between forms: kinetic energy, potential energy, thermal energy, chemical energy, electrical energy. They are all interchangeable, all measurable in the same units, all part of one conserved total. This means that every time anything slows down, every crate dragged across every floor, every pendulum losing its arc, every wheel grinding against its axle, the motion isn't being destroyed. It's being paid into a thermal account. The floor is the bank. The heat is the transaction record. Nothing's cancelled. Nothing is written off. The accounting is perfect, all the way down. There is something almost annoying about this, if you think about it from a certain angle, because it means the universe is extraordinarily careful, obsessively careful. It tracks everything, every joule of energy in every system at every moment, and it never, under any circumstances, lets any of it go missing. No exceptions, no rounding errors, no overlooked friction terms. This is not how human systems work. This is not how anything built by humans works. Things leak, budgets drift. Measurements are approximate. But the universe's accounting is exact in a way that starts to feel, after a while, less like a rule and more like a structural feature. As if precision isn't something the universe tries to maintain, it's something the universe simply is at this level. Joule, I think, would have appreciated that framing. He was precise the way some people are precise, and not because they're disciplined exactly, but because imprecision genuinely bothered them. Like a sound that's almost in tune, but not quite, and you can't stop hearing the gap. He presented his findings to the British Association for the Advancement of Science in 1843. They were, by most accounts, received with polite indifference. He was given very little time. He was not invited to speak the following year. He kept measuring anyway. There is a particular kind of stubbornness, not aggressive, not loud, just very hard to stop, that seems to be required for this type of work. The kind where the result is real but unspectacular, where the proof accumulates slowly and you can't point to a single decisive moment, where being right doesn't feel like anything for a long time. Joule had this. He improved his apparatus after each rejection. He narrowed his error bars. He extended his measurements to cover more systems, more methods, more materials. By the time the scientific community fully accepted what he'd been saying for years, he'd been saying it for years, the churning of the paddle through the water, the heavy, dull resistance of it, the faint warmth that accumulates in the barrel over the course of an experiment, not enough to feel with your hand probably, only enough to register on a calibrated thermometer held still in the water after the paddle has stopped. That warmth was the motion, exactly the motion, all of it. I find that I can sit with this in a way I couldn't when I first understood it. The idea that there is no loss anywhere, only translation, that the universe never forgets what it was given. That friction, which looks so much like cancellation, is actually just a very thorough conversion. An admission, finally, of where the motion was going all along. The paddle stopped. The water held the warmth. And somewhere in that exchange, measured obsessively by a brewer in a mid-century English town who smelled probably faintly of hops, the first law of thermodynamics was being written in degrees Fahrenheit, 1/100th at a time. Friction was the last place most people thought to look, and it turned out to be the most honest place in the room. the place where the universe showed its work if you had a good enough thermometer and the patience to wait. What happens when there's no friction at all, when motion has nothing to convert into and nothing to slow it, is a different kind of conversation. A pendulum in the dark swinging through the same arc over and over, in the kind of idealized quiet that only exists in physics problems and very still rooms at 3 in the morning. Picture a room with no light in it. Not dim, not the kind of dark where your eyes adjust and shapes emerge slowly from the grey. Proper dark, the kind that makes the room feel larger than it is, because you can't find the walls. A room like that, and in the middle of it, hanging from the ceiling on a thin cord, a pendulum. Nobody watching, no reason for it to be there. Just a weight on a string pulled to one side and released, and now it swings. You can't see it, but you could hear it maybe if the room were quiet enough. A faint displacement of air at the lowest point of the arc. The whispered resistance of the cord under tension. The weight is dense. Brass, say the old kind, the kind that's heavy for its size in a way that feels almost stubborn when you hold it. And it moves out to one side, pause at the top where it's neither arriving nor leaving, just hanging for a fraction of a second in a particular quality of stillness that is not rest. That is potential, pulled taut, waiting, and then back, through the centre, past the lowest point, up the other side. That same pause, that same instant of suspension, before gravity makes its claim again. Here is what's happening that you can't see. At the top of each swing, all the motion has drained out of the pendulum, and what remains is height. Just height. The weight hanging a few centimetres higher than it will be at the bottom, possessing in that position something the physicists call potential energy, which is not a thing in itself so much as a relationship. The relationship between the weight and the earth below it, the earth that wants it closer. All the energy the pendulum has is sitting in that relationship, quietly, invisibly, doing nothing that looks like energy at all. Then the weight begins to fall, not straight down, it can't, the cord won't allow it. So it falls in the only direction available, which is the arc, and as it falls the height drains out of it and speed builds in. The potential becoming motion, the stillness becoming swing. And at the lowest point of the arc, the height is fully spent and the speed is at its absolute most. The weight moving fastest where it is geometrically lowest. And then the arc carries it upward on the other side and the speed begins to give itself back, paying out into height again, climbing, all the way to the top, where it stops, and the height is back, all of it. This trade, height for speed, speed for height, back and forth, is what the pendulum does. This is the whole of it. And the extraordinary part, the part that's easy to hear as a physics fact and harder to actually feel as a truth about the world, is that nothing is lost in the exchange. Or, no, wait, that's not quite right. What I mean is the total doesn't change. The sum of what the pendulum has, all the height energy and all the motion energy together, at any moment in the swing, is the same number at the top as at the bottom, as at every point between. Different distribution, same total. The speed goes up as the height comes down. The height goes up as the speed comes down. The sum just persists in a frictionless system. In the darkroom, in the physics problem version of the darkroom, where the air offers no resistance and the cord has no stiffness and the pivot loses nothing to heat, there, the pendulum swings forever. Real pendulums don't swing forever. There's air, even very still air, and the weight has to push through it, and that pushing transfers some of the motion into the air molecules, which warm very slightly and carry the energy away in every direction until it's too spread out to do anything. And the cord flexes barely, and the pivot has some friction, and over time, over many, many swings, slowly, so slowly that you could watch for minutes before noticing, the arc shortens. The height at the top decreases, the speed at the bottom decreases correspondingly, the pendulum winds down. But not because the energy was destroyed, only because it left. Into the air, into the pivot, into the cord's slight internal warmth. The pendulum gave it away in small, quiet installments across hundreds of swings. And the room is the receiver, holding all of it, too dispersed to be useful, but there, all of it still there. There is something about watching, even imagining watching, a pendulum in the dark that feels different from being told a fact. I don't fully know why. Maybe it's the rhythm, the way it makes the exchange visible, or imaginably visible, one swing at a time, height to speed, speed to height, in a cycle slow enough that you can almost catch the moment of translation. At the top, it's clearly not moving. At the bottom, it's clearly not high. In between, it's clearly both. There's a moment, somewhere on the arc, where the energy is split evenly between the two forms, half height and half motion, and if you could freeze it there and look at it, you would be looking at a system that is, in that instant, exactly balanced between what it was and what it's about to become. That moment exists on every swing. It passes in a fraction of a second. Most things that exist on every swing of something and pass in a fraction of a second go completely unnoticed. This one is, I find myself wanting to say it matters, but that's the wrong framing. It doesn't matter in any practical sense. It just is. It happens every time. The universe executes this trade with a perfect fidelity every single swing, in every pendulum, in every system where potential and emotion are exchanging, and it never gets any of it wrong. The room is still dark. The pendulum is still moving, slower now, the arc a little shorter, the pauses at the top a little less dramatic, but still moving, the weight still tracing its path through the dark air, still making that faint sound at the lowest point, still carrying out the exchange. At some point, hours from now, or days if the room is sealed and cold and the pivot is very smooth, it will stop. The arc will have narrowed to nothing, the weight will hang straight down, and the room will be, in total, an amount warmer than it was, very slightly, unmeasurably to anything you own. But by exactly the energy the pendulum started with, exactly that amount, distributed into the air and the cord and the pivot and the ceiling above it. Nothing was used up, everything was redistributed. The weight hangs still, the room holds the warmth that it was given. In the patient way rooms hold things, without acknowledgement, without ceremony, just incorporated into whatever the room is now. The temperature is different by a quantity too small to name in any normal conversation. The pendulum is done, but the pendulum's energy isn't done, isn't gone. It's just stopped being a pendulum and started being the room. The specific temperature of a specific cubic meter of air in a dark room that once held something swinging, that's all it is now. That and the accounting, which is, as always, exact. He was 22 years old and already measuring things nobody had asked him to measure. That's the detail that stays with me. Not the discoveries, not the eventual recognition, which came late and partially and never quite completely in his lifetime, but the image of a 22-year-old in a brewery in Salford, surrounded by fermentation vats and the low persistent smell of malt, running experiments on the side because the questions wouldn't leave him alone. Nobody assigned him this. Nobody funded it in any meaningful sense. He had a brewery to run and he ran it, and then, apparently in whatever time remained, he built increasingly precise instruments and used them to chase a number that most of his contemporaries didn't think was worth chasing. James Prescott Joule was not, by the standards of the era, a scientist. Not credentialed, not affiliated, not in the right rooms. He was a manufacturer's son who'd received some private tutoring from John Dalton. Yes, the atomic theory Dalton, which is a remarkable biographical coincidence that seems almost too neat to be true, and then gone into the family business. The family business happened to be beer. Salford in the 1840s was not a pleasant place to be, particularly. The air carried coal, particulate and river damp, and the kind of pervasive industrial greyness that photographs from the era seemed to almost generate on their own, as if the chemistry of old photography and the chemistry of Victorian English mill towns were in natural sympathy. The brewery was on New Bailey Street. The equipment was heavy, mechanical, maintenance-intensive. Joule managed employees, dealt with suppliers, handled the financial side of a working commercial operation. And then, presumably when everyone else had gone home, he went back to the experiments. What drove him specifically was electromagnetic engines. He was interested early on in whether electric motors could replace steam engines in industrial settings, a practical question with practical stakes given that the brewery ran on exactly the kind of machinery he was asking about. He built small electric motors and tested their efficiency, and what he found doing that was that the heat produced by the motor's resistance seemed to be not incidental, not a loss to be minimized, but proportional to something, related to something. The heat wasn't random waste, or it was obedient. It followed a rule. I find this part genuinely interesting, and it's easy to miss in the standard account. This is where his obsession started. Not with some grand philosophical question about the nature of energy. With an electric motor in a brewery it was, and the stubborn, specific way the heat it produced refused to be accidental. The law he worked out from those early motor experiments is now called Joule's first law, though that name is not used much anymore. It says that the heat produced by an electrical conductor is proportional to the square of the current and to the resistance of the conductor. It's precise in the way physics laws are precise. Not an approximation, not a tendency, a fixed relationship. Double the current, quadruple the heat. It has that quality of genuineness that physical laws have when they're really true, which is they don't give you any wiggle room. He published this in 1841. He was 22. The reception was, well, polite silence is perhaps the most accurate description. The physical society he sent it to declined to publish the full paper. He kept going anyway, which is the recurring fact about Joule that I don't quite know how to hold properly. He kept going in a way that doesn't seem to have been fueled by bitterness or defiance. Or maybe it was, and the historical record just doesn't show it, but comes across more like the behaviour of someone who's following something real, and therefore cannot stop following it, regardless of what the reception is. By the mid-1840s, the experiments had moved from electrical heating to the question that would define his career, the mechanical equivalent of heat. How much work does it take to produce a measurable quantity of heat? Is the ratio fixed? Is it always the same no matter what method you use to convert work to heat? The paddle wheel apparatus is the famous one. It's the one in the textbooks, the one reproduced in demonstration equipment in physics departments to this day. A calorimeter. A paddle wheel inside it, a cord, a falling weight. The weight falls, the paddle churns the water warms. Joule measures how much. He measures it again. He changes the weight, the height of fall, the design of the paddle, the amount of water. He gets the same ratio every time. He did this in a brewery, with, one presumes, all the temperature variability that a working industrial building in northern England involves. The fact that he got consistent results under those conditions says something about the stubbornness of physical law, and something about the stubbornness of James Joule, and I'm genuinely not sure which one it says more about. The number he arrived at, the mechanical equivalent of heat, was approximately 772 foot-pounds of work per British thermal unit of heat. In modern terms, 1 calorie of heat requires about 4.18 joules of mechanical work to produce. Joule's experimental value was within 1% of this, within 1%. With wooden paddles and a hand-wound weight and a thermometer in a brewery in Salford. I want to be careful about what I'm saying there, because it's easy for this to become a kind of marvel at the Victorian genius moment, which is not quite the point. The point is that the physical law Joule was measuring is so consistent, so exact, that even relatively crude instruments will converge on the truth if you're careful enough and patient enough and willing to run the experiment enough times to wash out the noise. The truth was there to be found. Joule found it because he kept looking. He presented his results at the British Association meeting in Oxford in 1847. Was allocated very little time, 50 minutes, something like that, and apparently told to be brief, rather than read his paper in full. A 28-year-old brewer in a room full of professional scientists, asked to summarize years of careful work in the time it takes to drink a cup of tea. He was brief, and then a young man in the audience, 23 years old, already recognized as exceptionally able, already something of a rising figure in British natural philosophy, asked a question, not a dismissive question, a real one, the kind that signals genuine engagement, genuine interest, the kind that comes from someone who has understood what was just said and wants to understand it further. The young man was William Thomson, who would later become Lord Kelvin, who had significant reservations about Joule's conclusions, but who clearly took them seriously from that first exchange. Thomson and Joule began a correspondence, and then collaboration of sorts, that went on for years, and the friction between their views, the slow movement of Thomson's position from sceptical to convinced to advocate, produced more clarity on the subject than either of them might have managed alone. Joule had the experimental results. Thomson had the theoretical framework to understand what the results meant. The two things together were harder to argue with than either one separately. The specific claim Joule was making, not just that work could produce heat, but that the conversion was fixed and perfect and complete, that no work was lost in the translation, that the heat produced always equaled exactly the work put in. This was the part that took the longest to accept, because it implied something large. It implied that heat was not a different kind of thing from work, not a different substance, not a different category of physical reality, just the same capacity, the capacity to cause change, wearing a different coat, which meant energy was conserved, not just sometimes, not in special cases, always, everywhere, in every system, across every possible transformation. The number never changed. It only moved. Joule didn't state the first law of thermodynamics in so many words. He was an experimentalist, not a theorist, and grand formulations weren't really his idiom. He measured things, he reported the measurements. He trusted the measurements to speak for themselves. They did, eventually. It just took a while for the room to get quiet enough to hear them. He died in 1889, by which point the unit of energy had been named after him, the Joule, though he was apparently characteristically modest about this, or at least not visibly delighted by it in any documented way. He had received honours late, the Royal Society eventually, the recognition of peers who had once ignored him, a small pension from the government in his later years when the brewery business had declined and he was not wealthy, The thermometers he used in his most careful experiments were extraordinarily good for their time. Some of them are in museums now. Objects of a particular kind of beauty, not decorative beauty, functional beauty. The beauty of a thing made to do one job with as much precision as the maker could achieve. Long and thin, sealed at the top, with graduations so fine you'd need good light and patience to read them. He carried one of these on his honeymoon to Switzerland in 1847, measured the temperature of a waterfall, Cascade de Salanges near Chamonix, at the top and at the bottom. Found it slightly warmer at the bottom by approximately the amount you'd predict if the falling water's kinetic energy had converted to heat on impact with the rocks below. His wife was apparently present for this. Her opinion of the thermometer and the waterfall measurements is, as I mentioned, not in the historical record. I find myself hoping she found it endearing. She may have found it exhausting. Both seem like reasonable responses to marrying someone who brings calibrated thermometers to waterfalls on honeymoons. The consistency of Joule's number, the way it refused to change no matter how many times or in how many different ways he tried to produce heat from work, is, in retrospect, the most significant thing about his experiments, not just as a measurement, but as a kind of evidence about the nature of the universe. A ratio that never changes is a law that holds across every system, every method, every material, every scale. That's something more than a generalization. It's a structural feature. Something about the way reality is built that makes this particular trade, motion to heat, work to warmth, happen at exactly this rate and no other, regardless of the path between them. Joule didn't know why. He knew that it did. The why, the deep mathematical reason beneath the consistency, the reason it couldn't be any other way, was still half a century away, waiting for a mathematician in Göttingen who would connect it to something much larger than waterfalls or paddle wheels or the temperature of water in a brass container. But the brewery is where it was found. Not in a university, not in a laboratory built for the purpose, though, in a working building that smelled of fermentation and coal smoke, and whatever the English Midlands smelled like on a cold afternoon in the 1840s, which I imagine was something dense and mineral and slightly wet. Joule's number held in that building. It held in the Swiss mountains with the waterfall. It held in every physics department that has reproduced his experiment in the century and a half since. It holds right now in every system converting any form of energy into any other form, silently and without exception, the way things hold when they are not rules someone made up but features of the territory. Everything he touched got warm, exactly the amount it was supposed to. Something was missing. Not metaphorically, not in the vague sense of an incomplete understanding or a gap in theory that might eventually be filled. Something was measurably, quantifiably, stubbornly absent from an experiment that should have accounted for everything. Numbers went in, smaller numbers came out. The difference sat there in the data like a hole in a table, not subtle, not ambiguous, just wrong. This was the 1920s. Conservation of energy was not a new idea by then. Joule had done his paddle wheel experiments 80 years earlier. The first law of thermodynamics had been formalized for decades. The principle that energy is conserved, that you cannot run the accounting and come up short, was as close to settled as physics gets. Not an axiom exactly, but close enough to one that finding an exception would have been, well, finding an exception would have been the kind of thing that breaks a field open at the seams. The experiment in question involved beta decay. Beta decay is a process where certain atomic nuclei are unstable, twitchy, restless, sitting in a configuration that costs more energy than the universe wants to maintain. And they resolve that instability by ejecting an electron. The nucleus changes, the electron flies out, the atom becomes a different element. It happens constantly in radioactive materials, in the walls of certain buildings, in the potassium in your body right now, unremarkably all the time. When physicists measured the energy of the ejected electron, they expected a specific value. The nucleus before, the nucleus after, the difference in energy between those two states had to go somewhere, and the electron was the only thing leaving, so the electron should carry all of it. Same amount, every time, fixed, predictable. It wasn't. The electrons came out at a range of energies. Some had most of the expected energy. Some had much less. Some had barely any. The distribution was continuous, a smooth spread across a range of values, which meant there was no obvious secondary particle, no hidden thing carrying off a fixed portion. Just a smear of energies, none of them consistently right, all of them adding up to less than they should. The data was not ambiguous. The data was, by the standards of experimental physics, extremely clean. The missing energy was real, consistent, reproducible. Something was wrong. For a moment, and this is the part that most accounts of this story rush past, which I think is a mistake, for a genuine, extended, professionally uncomfortable moment, physicists considered the possibility that conservation of energy was simply not true. Not just approximately true or true in classical systems, but violated at the quantum scale. Actually, fundamentally not a reliable law of nature. Niels Bohr, who was not prone to casual theoretical abandonment, who was one of the architects of quantum mechanics and not someone who discarded principles lightly, Bohr suggested seriously and in print that energy conservation might be statistical rather than exact at the subatomic level, that it might hold on average across many events without holding for each individual event. This is the kind of suggestion that sounds very calm when written in a physics paper and is, in fact, seismic. It would have meant that the universe plays fast and loose with its own accounting at small scales, that the careful exactness Joule measured in water and falling weights was a large-scale average of quantum sloppiness beneath, that the law Joule found wasn't a structural feature of reality but a kind of emergent tidiness from disorder below. Bohr was wrong, but he wasn't obviously wrong. The missing energy was real, and it needed explaining, and Bohr's explanation was coherent. It just happened to be incorrect. Wolfgang Pauli was not comfortable with Bohr's position. Pauli, who was brilliant in a way that was apparently somewhat difficult to be around, who had a reputation for intellectual sharpness that left marks, who once described a paper he reviewed as not even wrong, meaning it wasn't even coherent enough to be falsifiable. Pauli looked at the beta decay data and came to a different conclusion. He did not think energy conservation was broken. He thought something was hiding. He proposed in a letter in 1930, not a paper, a letter, because he apparently wasn't confident enough in the idea to formally publish it, which is a detail I find unexpectedly humanizing about someone of his stature, that there was a second particle being emitted in beta decay, something that carried off the missing energy, something electrically neutral with very little or perhaps no mass, that passed through ordinary matter without interacting with it, undetected by every instrument available at the time. He called it provisionally the neutron. The name was later changed. Enrico Fermi renamed it the neutrino, the little neutral one, after James Chadwick discovered the actual neutron in 1932, and the name was needed for something else. The neutrino Pauli proposed was, at the time of its proposal, entirely hypothetical. There was no direct evidence for it, no detection, just the energy is missing. Something must be carrying it. Here is what that something would have to be in order for the numbers to work. Pauli reportedly said in the same letter that he'd done a terrible thing by proposing a particle that could not be detected. He was not being falsely modest. He meant it. A particle that passes through everything, that leaves no trace, that interacts with matter so weakly that detecting it seemed practically impossible. This was the kind of thing that made other physicists uncomfortable, because it felt less like a scientific hypothesis and more like a theological one, an invisible thing that you need to exist for the books to balance. Outside, somewhere, a dog is barking at something and then stopping, and the silence after is the particular quality of silence that follows a sound, not empty, still carrying the shape of what just ended. The room is very dark at this hour, the kind of dark that makes thinking feel slightly different, slightly less linear, back to the particle that was everywhere and nowhere. The discomfort the neutrino hypothesis produced was, I think, philosophically reasonable and scientifically wrong, which is not a combination that's unique to this case. Science is full of hypotheses that felt methodologically uncomfortable and turned out to be true, but it's a combination worth sitting with, because the discomfort was coming from a good instinct taken one step too far. The instinct was, don't invent entities you can't detect to patch holes in your accounting. This is a genuinely important heuristic in science. Phlogiston was, in a sense, an invented entity patching a hole in the accounting of combustion. The ether was an invented medium patching a hole in the propagation of light. Both were wrong, both were invented to make the numbers work, and neither was real. The neutrino felt like that, an accounting trick dressed as a particle. Except that Pauli's proposal was different in one critical way. It made specific falsifiable predictions. The neutrino, if it existed, would have to have specific properties, specific spin, specific relationship to the electron, specific effect on the momentum of the nucleus. These weren't vague requirements. They were constraints that could, in principle, be tested if instruments ever became sensitive enough. It took 26 years. In 1956, Clyde Cowan and Frederick Reines detected the antineutrino experimentally, using a nuclear reactor as a source of the enormous flux of particles needed to get even a handful of interactions out of something that barely interacted with anything. The experiment involved a tank of water and cadmium chloride, and it was the kind of experiment that requires extraordinary patience and a high tolerance for the possibility that nothing will happen regardless of how long you wait. Something happened. The signal was unambiguous. The neutrino, Pauli's invented accounting particle, the ghost he'd apologized for proposing in 1930, was real, had always been real, had been carrying off the missing energy in beta decay all along, passing through every instrument that had ever tried to catch it, flying through the earth and the sun and the bodies of everyone who had ever wondered where the energy went. Pauli was alive to hear this. He was sent a telegram. His response, by various accounts, was something like profound relief. The relief of someone who has been holding a conviction for 26 years without the ability to prove it, and who has finally been told that the conviction was justified. The energy had never been missing. There is something in this story that matters beyond the neutrino itself, beyond the specific particle and the specific decay and the specific experiment. What matters is what the physics community did not do. They did not discard conservation of energy when the numbers came out wrong. Most of them, Bohr notwithstanding, kept the principle and looked for what they were missing. They treated the gap not as evidence that the law was broken, but as evidence that something was hiding. That is, I want to be careful about how I say this, because it could sound like I'm arguing that scientists should believe things without evidence. But that particular choice, the choice to trust a deep structural principle even when one set of experiments seemed to violate it, was not blind faith. It was pattern recognition. Conservation of energy had been confirmed so many times in so many different systems that a single class of experiments producing a wrong number was more plausibly explained by something undetected than by the law being wrong. The law was a better bet than the data, and the law won. Something invisible passes through you constantly. Billions per second are billions, a genuinely absurd number. Neutrinos from the sun, from distant supernovae, from the natural radioactivity of the Earth, from nuclear reactors on the other side of the planet. They pass through the wall, through the bed, through you, and continue outward, through the floor and the rock and the mantle of the Earth, and out the other side without so much as noticing you were there. They are carrying energy. They have been carrying energy since the first nuclear reactions in the sun, 8 minutes ago by light's travel time, longer by the age of the cosmos. They are part of the accounting. They were always part of the accounting. The books were never unbalanced. The universe was just holding some entries in a column no one had learned to read yet. And when Cowan and Reines finally saw the signal in their tank of cadmium water. Late in 1956, what they were seeing was not a discovery exactly and not a new thing being added to the ledger, but the ledger finally becoming legible. The missing energy had never been missing. It had been there, patient, passing through everything, waiting for someone to build an instrument capable of noticing it at all. Your hand is resting on something right now, a blanket maybe, the edge of a pillow, the smooth give of a mattress under the slight weight of an arm that has stopped being held up. Whatever it is, it has mass. It has the property of being there, of taking up space, of resisting being moved, of being, in the most fundamental physical sense, present. That presence, that there-ness, it is not what it appears to be. Mass before the 20th century was the end of the conversation. You wanted to know what something was made of. You found its mass. You wanted to know how it would respond to a force. Mass told you. It was the fundamental measure of matter, the thing that made matter matter, and it was its own category, not energy, not motion, not heat, its own thing with its own conservation law. Mass is neither created nor destroyed. This seemed unassailable. It still seems unassailable if you live at the scales where most of life happens, the scales of falling objects and burning wood and paddle wheels in barrels of water. At those scales, mass is conserved. You can check, burn a log in a sealed container, collect everything, gases, ash, water vapour, and the total mass is the same before and after. It was Lavoisier who demonstrated this, carefully, in the late 18th century, and for a long time it held without exception. It still holds approximately. The approximately is the thing. When you burn wood, some mass actually does become energy. The carbon and oxygen forming new bonds in CO2, that process releases energy, and the energy has mass, and the mass of the products is slightly less than the mass of what you started with, by an amount so small that no scale Lavoisier owned, no scale anyone owned before the 20th century could possibly have detected it. The difference for a log fire is something like a billionth of a gram. A billionth of a gram in a burning log. The conservation of mass holds in a chemistry lab because the violation is that small. But in a nuclear reaction, the difference isn't billionths of grams, it's measurable, significant. In nuclear fission, the splitting of a heavy nucleus, the products weigh less than the original nucleus by about 0.1% of the total mass. Which sounds small, it isn't. Because what that missing mass became is energy, and the rate of exchange is the speed of light squared. The speed of light is roughly 300 million meters per second. Squared. That's approximately 90 quadrillion. 0.1% of the mass of a uranium nucleus, multiplied by 90 quadrillion is, well, it's why nuclear weapons exist and why nuclear power plants produce the output they produce, and why the sun has been burning for 4.5 billion years without running out of fuel. A very small amount of mass is an incomprehensible amount of energy. That ratio is what E=mc² means. But I want to stay with something before moving on, because the equation is easy to state and hard to actually absorb. What it says, underneath the algebra, under the compact notation, is that mass is not a different thing from energy. Mass is energy, in a particular form. The way ice is water in a particular form— no, wait, that's not quite right. That analogy does something slightly wrong to the concept. Mass is more like energy at rest. Energy that has settled into a stable configuration, that isn't moving anywhere, that isn't radiating outward, that is simply sitting in the structure of matter and waiting. Not metaphorically waiting, physically waiting, available, convertible. The mass of a proton is almost entirely the energy of the interactions between its constituent quarks. The gluons holding it together carry energy, and that energy contributes to the mass of the whole. The proton is not mostly stuff. It is mostly a set of energy relationships configured in a way that has the property of mass. Pull the configuration apart, change the relationships, and some of that mass can become kinetic energy, photons, heat, whatever the geometry of the interaction allows. The thing sitting quietly in ordinary matter, doing nothing, is energy in an extraordinarily patient posture. Einstein arrived at this in 1905 in a paper that was, by historical accounts, somewhat anticlimactic in its reception. It was one of 4 papers he published that year, in what is now called his Annus Mirabilis, his miracle year, and the one about special relativity got more immediate attention than the short follow-up paper that contained, almost as a corollary, the mass-energy relationship. The follow-up paper was 3 pages long. It derived from the principles of special relativity that if a body emits energy in the form of light, its mass must decrease by the energy divided by the speed of light squared. And therefore, the step felt almost obvious once the setup was in place. Mass and energy were the same thing, 3 pages. Einstein himself was apparently uncertain for a while about whether the result was correct. He wrote to a friend that he was not sure whether God was leading him around by the nose, which is, from the man who said it, a remarkable thing to have written. Even he wasn't immediately sure this was real. The heavy wool smell of a blanket, the specific warmth where it's been touched for a while and holds the heat, that physical detail of the thing resting in your hand right now. The blanket has mass. It contains, locked in the bonds of its cotton or wool or synthetic fibres, in the interactions of the atoms it's made of, an amount of energy that, if converted entirely, would be— you don't want to know actually. Or maybe you do. A 1 kilogram object converted entirely to energy via E=mc² would release approximately the same energy as a 20 megaton nuclear weapon. The blanket weighs more than a kilogram. This is not dangerous information. That conversion cannot happen at room temperature. It cannot happen with any chemistry or most physics. It happens in conditions that are not present in your bedroom. But the energy is there, real, sitting in the mass, in the molecular bonds, in the quark interactions, in the structure of everything ordinary. All of it is energy holding a particular shape. What this means for conservation of energy is, it enlarges it. That's the word I keep coming back to, even though it's not quite technical enough. Before Einstein, conservation of energy and conservation of mass were 2 separate laws running in parallel, both confirmed, both trusted. What relativity showed is that they were never 2 laws. They were always one law with a more complete version waiting to be found. energy is conserved. Mass is a form of energy. Therefore, the conserved quantity is mass energy, the total, the unified thing. And at everyday scales where nuclear reactions aren't happening, the mass part stays constant and the energy part stays constant. And it looks like two separate laws, but it was always one. The law didn't change. The understanding of what it was conserving got bigger. There's something I find genuinely strange about this. Not troubling, just strange in the way that certain truths are strange when you hold them directly, which is that the solidity of everything, the thingness of things, the quality of matter that makes it feel like the opposite of energy, is itself energy. The table is energy. The wall is energy. Your hand is energy in a configuration that has lasted without much changing for however many years you've been alive, and will continue in that configuration for some time more, and will eventually, slowly through chemistry, through the patient work of entropy, convert into other configurations, other distributions, all still energy, none of it disappearing. Mass isn't the end of the story. It isn't even a different story. It's the same story in a different chapter. And the chapter is a long one, and the energy inside it is unimaginably patient. It waits in the matter the way potential waits in the pendulum at the top of its arc. Not doing anything visible, not going anywhere, just present, available, held in a configuration that the universe maintains with its characteristic exactness. The blanket on your hand has not moved. The energy in it has not changed. It is simply being right now in the form of matter, and that is a thing that looks like rest, and is, in some deeper sense, nothing of the kind. What holds all of this together? The reason this conversion is possible at all? The reason the exchange rate is what it is? The reason any conservation law exists at anything deeper than coincidence? Is a question that waited for a quiet woman in Göttingen who understood symmetry better than almost anyone alive. Pick up a rock and put it down somewhere else. The rock falls the same way. Same arc, same acceleration, same impact. The laws governing its fall didn't change because you moved it 3 feet to the left. You could move it 3 miles or 3,000 miles and the physics would be identical. The same gravitational relationship, the same equations, the same result. The laws of physics don't care where you are. That indifference, that sameness across location, is a symmetry. Spatial translation symmetry technically, but before it's a technical term, it's just a fact about how the world behaves. The rules are the same everywhere. Most people encounter this as obvious. Of course the rules are the same everywhere. What would it even mean for them not to be? If gravity worked differently in different places, if the laws shifted depending on your coordinates, the universe would be a fundamentally different and considerably stranger kind of place. The consistency of physical law across space feels less like a discovery and more like a baseline assumption, the minimum requirement for there to be a universe with coherent behavior at all. But consistency across space is a specific symmetry, and there is another symmetry running parallel to it. That is less immediately obvious because we live inside it and have no reference point outside it. The laws of physics are the same today as they were yesterday. They will be the same tomorrow. An experiment run now produces the same result as the same experiment run last Tuesday. Not approximately, not usually, but always exactly as far as anyone has ever been able to test. Physics doesn't age. The equations don't drift. Tuesday's gravity is Monday's gravity is the gravity of 1 billion years ago, applied to whatever matter existed then in whatever configuration it occupied. This is time translation symmetry. The laws are invariant under shifts in time. It seems, again, obvious, until you ask what follows from it. Emmy Noether asked what follows from it. She was born in 1882 in Erlangen in Bavaria, the daughter of a mathematician. Her father, Max Noether, was a professor, which meant she grew up in a home where mathematics was the air rather than a subject, and she was, by any measure, extraordinarily able from early on. She completed the equivalent of a teaching certification in French and English, because that was the path available to women at the time, and then, apparently finding language instruction insufficient as a life's work, she attended university lectures in mathematics as an auditor, because women could not formally enroll. She passed the graduation examination anyway. She completed a doctorate at the University of Erlangen in 1907, one of the very first women to do so at that institution. Then she spent years doing mathematics without a paid position, because the faculty wouldn't hire a woman. She lectured occasionally under her father's name. She worked, she produced results. The university's academic senate when Hilbert and Klein proposed her for a faculty position at Göttingen in 1915, was reportedly told by one dissenting member that soldiers returning from the front would be unwilling to study under a woman. Hilbert's response to this, by various accounts, was something like, "This is a university, not a bathhouse. The gender of the applicant is irrelevant to the quality of the mathematics." He did not win the argument. Noether was not given a faculty appointment. She lectured anyway, listed in the course catalogue under Hilbert's name, and continued producing some of the most significant mathematics of the century. The specific problem she was working on in 1915, the one that produced the theorem, was a genuine crisis in physics. Einstein had just published general relativity, and it was becoming clear that the new theory had a peculiar relationship with energy conservation. In general relativity, where space-time itself curves and shifts in the presence of mass and energy, the straightforward version of energy conservation seemed to break down. The energy in a gravitational field was difficult to define locally. The numbers weren't obviously balancing. Hilbert and Klein, who were among the people working on this, brought Noether in specifically because she understood invariance theory, the mathematics of what stays the same when things change, better than anyone they knew. She was supposed to help them understand what was happening with energy in general relativity. She did that, and incidentally proved something much larger. The proof she published in 1918, two theorems, the first of which is the one that changed physics, says, stripped of its mathematical formalism, something like this. Every continuous symmetry of a physical system corresponds to a conserved quantity. Every symmetry a conserved quantity. Not as a coincidence, not as a useful pattern, as a mathematical necessity. If the symmetry exists, the conservation law follows from it the way a shadow follows a shape. You cannot have one without the other. Spatial symmetry, the laws are the same everywhere, gives you conservation of momentum. Rotational symmetry, the laws are the same regardless of which direction you're facing, gives you conservation of angular momentum. And time symmetry, the laws are the same today as yesterday, gives you conservation of energy. There is a cup of cold tea on the desk somewhere, gone cold during the writing of something, and it has been sitting there long enough that a faint ring has dried on the outside where the heat briefly condensed. A small ordinary object radiating its final warmth into a room that doesn't need it. Conservation of energy is not a rule the universe follows. It is a consequence of the fact that the universe's rules don't change with time. It is what time symmetry looks like when you translate it into quantities. If physics were different on Wednesdays, if the equations shifted even slightly between one day and the next, the energy would not be conserved. It would leak or accumulate between the different physics Tuesday and the different physics Wednesday. The conservation law would dissolve. The law exists because time is uniform, not the other way around. This is the part that I think physics education usually gets slightly wrong, and I say this aware that I am not a physicist and this is a personal reading of a pedagogical pattern, by teaching conservation of energy as a foundational axiom, a starting premise, the thing you accept before you do the work. Noether's theorem suggests it isn't that. It's a derived result. It sits downstream of something deeper, the symmetry of time, the plain and verifiable fact that the universe is running the same code today that it ran yesterday. Conservation of energy is what that symmetry looks like in units of joules, which means, and this is the implication that I find hardest to fully absorb, that asking why energy is conserved is the same question as asking why the laws of physics are stable across time. And the answer to that is not something physics can fully reach. Physics can verify the stability, can test it to extraordinary precision, can show that nothing in any experiment has ever suggested the laws are drifting. But why the laws are time-symmetric in the first place, why the universe is the kind of universe where Tuesday's gravity is Monday's gravity, that sits at the edge of what the framework can explain about itself. Noether's theorem doesn't answer that. It just makes the question precise. She was dismissed from her position at Göttingen in 1933 when the Nazis came to power and expelled Jewish faculty. She went to Bryn Mawr College in Pennsylvania, where she taught for less than 2 years before dying of complications from surgery in 1935. She was 53. Einstein, in an obituary notice in the New York Times, called her the most significant creative mathematical genius thus far produced. The phrasing is slightly clumsy. Thus far produced has a transactional quality that sits oddly in a memorial, but the assessment was genuine. She had transformed abstract algebra, group theory, ring theory, and the theoretical foundations of physics, often without stable employment, often under conditions that would have stopped most people entirely. The theorem that bears her name is taught in most physics curricula as a technical tool, a method for finding conserved quantities from symmetries useful, important, move on. The depth of what it says is often left unexamined, which is, I understand why, there's a lot of physics to cover. But something is lost when you skip past it. What it says is that conservation laws are not arbitrary features of the universe. They are not a collection of facts. Energy does this, momentum does that happen to be true and could, in some other universe, be otherwise. They are structural necessities. They follow from symmetries that seem, in turn, to be fundamental to what it means for a universe to have consistent laws at all. The conservation of energy is the universe's way of being the same kind of place it was yesterday. It has been that same kind of place, as best anyone can measure, for 13.8 billion years. The cold tea is still cold. The ring on the outside of the cup is still there. The warmth that left it an hour ago is somewhere in the room, in the air, in the surface of the desk, in the thin convective currents that have long since merged with everything else. All of it still accounted for. All of it still there. Because today's physics is yesterday's physics. Because the laws didn't change while the tea was cooling. Because Emmy Noether proved in a paper published in a year when she didn't have a faculty position and couldn't formally teach under her own name, that these two facts are not separate facts at all. They are one fact, seen from different angles. The stars keep that accounting too, and they spend it in a way that makes everything else possible. Slowly, over billions of years, converting mass to light, sending energy outward in every direction, most of it into the cold of space and some of it, a very small fraction, arriving somewhere that happens to matter. The sun is not on fire. This matters, and it's one of those corrections that sounds pedantic until you sit with what it actually implies. Fire is chemistry, carbon and oxygen forming new bonds, releasing the energy stored in old ones, producing heat and light and CO2, and the particular smell of things combusting. Fire needs fuel, and it needs oxygen, and it runs through both at a measurable rate, and when either runs out, the fire ends. The sun has no oxygen to speak of, not in its core, not where the energy comes from. What it has is pressure, gravity pressing inward on a mass of hydrogen so enormous, 2 billion kilograms, a number so far outside normal scale it essentially stops meaning anything, that the core reaches temperatures of 15 million degrees and densities so extreme that matter stops behaving like matter and starts behaving like something for which ordinary language has no particularly good words. Under those conditions, hydrogen nuclei, bare protons, stripped of electrons moving at speeds that would be incomprehensible at room temperature, collide with enough force that they don't bounce, they fuse. 4 protons come together through a sequence of reactions and become one helium nucleus. And the helium nucleus weighs slightly less than the 4 protons did separately. That missing mass becomes energy. The rate of this conversion is, depending on how you look at it, either staggering or remarkably restrained. Every second, the sun converts roughly 4 million metric tons of mass into energy. 4 million tons of matter simply ceasing to be matter and becoming instead electromagnetic radiation. Gamma rays primarily hard and energetic, born in the core at temperatures that would instantly destroy any material object you could name. 4 million tons per second sounds like a fire burning fast. It isn't. The sun has been doing this for 4.5 billion years, and has enough hydrogen remaining to do it for roughly another 5 billion. The rate of conversion relative to the total available fuel is extraordinarily slow, slower than a candle if you normalize for mass. A human body, pound for pound, produces more heat through metabolism than the sun's core produces through fusion. The sun's power comes from its size, not its intensity. This is not how most people picture it. The sun feels intense, stepping outside on a clear summer day, in a place with no shade, the specific pressure of direct sunlight on the back of the neck. The way surfaces left in it become too hot to touch. And that intensity suggests a furious process at the source. But the source is patient. The sun spends its fuel with extraordinary care. It has been spending it since before the Earth existed, and will continue spending it until after anything we recognize as life has ended. The gamma rays born in the core don't leave immediately. This is the part of the story that tends to produce a specific kind of quiet discomfort when you hold it properly. The photons generated by fusion in the solar core, the direct products of hydrogen becoming helium, the immediate carriers of that converted mass energy, don't travel outward in a straight line to space. They can't. The solar interior is so dense, so crowded with matter, that a photon travels only a fraction of a centimeter before being absorbed by another particle, which re-emits it in a random direction, which travels another fraction of a centimeter and is absorbed again. This process, the photon random walking outward through a medium so opaque it makes lead look transparent, takes time. The estimates vary depending on the model of the solar interior, but the range is somewhere between 10,000 and 100,000 years, possibly longer. A photon born in the core today will wander, absorbed and re-emitted, deflected and redirected through the radiative zone, which extends from the core to about 70% of the way to the surface, for timescales that make human history look like a brief interruption. 10,000 years ago, humans were transitioning from nomadic to agricultural life in the Fertile Crescent. Whatever photon is currently leaving the sun's surface was, 10,000 years ago, at minimum somewhere deep in the interior, beginning its slow interrupted journey outward. This is the patience of stellar physics, not metaphorical patience, actual physical patience built into the structure of the material. The energy doesn't change during this journey, it shifts form, gamma ray to X-ray to ultraviolet as successive absorptions and re-emissions gradually cool the effective temperature of the radiation, but the total is conserved. Every absorption transfers energy to the absorbing particle. Every re-emission returns it to the radiation field. The accounting continues, uninterrupted, across 100,000 years of random wandering through the solar interior. At the convective zone, the outer 30% of the Sun, where the material is less opaque and heat moves by actual physical churning of plasma rather than radiative transfer, the energy moves faster. Hot plasma rises, dumps its energy near the surface, cools, sinks, rises again. Convection cells the size of small countries, cycling constantly, carrying the energy the final distance to the photosphere. The photosphere is where the Sun becomes transparent, where photons, for the first time in their 100,000-year journey, can travel without being immediately reabsorbed. They leave into space. Space is, in the relevant sense here, nothing. No medium, no absorption, no scattering except by the occasional particle in the very thin solar wind. A photon leaving the photosphere travels at the speed of light, obviously, which means it crosses the 150 million kilometers between the Sun and Earth in approximately 8 minutes. 8 minutes, after potentially 100,000 years inside the Sun. The ratio of those two numbers is something I find genuinely difficult to hold in any useful way, not as a failure of comprehension, but as an indicator of the extreme difference between the two environments. Inside the Sun, maximum density, constant interaction, geological timescales to travel a solar radius. Outside, vacuum, no interaction, 8 minutes to travel 150 million kilometers. The photon that arrives at Earth has no memory of its journey. It carries no record of the 100,000 years and the billions of absorptions and re-emissions. It arrives as visible light, in a narrow band of wavelengths that correspond to the Sun's surface temperature, around 5,500 degrees Celsius, and it has been 8 minutes in transit, and in some sense it has been 100,000 years and 4.5 billion years in the making, depending on where you start the accounting. What it carries is mass energy, the specific fixed amount that was converted from hydrogen to helium in the core, minus whatever was lost to neutrinos, and neutrinos carry away about 2% of the total energy in the proton-proton chain, passing through everything without interaction, as they always do. The remainder riding outward as radiation, changing forms slowly across the interior, arriving finally as the particular wavelengths of visible light that human eyes evolved to detect. It arrives eventually somewhere, the back of a hand perhaps, resting near a window in the early morning, when the light is coming in at a low angle, and the quality of it is warm and slightly golden, and has that specific quality of morning light that is different from afternoon light in a way that's hard to articulate but immediately recognizable. The photon is absorbed by the skin. A tiny amount of energy, 1 photon's worth, which is a quantity so small it has no analogy at the scales we normally think in, transfers to the tissue. Warmth, the faintest increment of warmth, the kind you feel only if you're paying attention. That is the end of the journey, not a spectacular end, not commensurate with the time scale, a photon that took 100,000 years to escape the solar interior. Arrives at hand near a window in the space of 8 minutes, and deposits its energy as an amount of heat too small to measure with any instrument you own. But the energy is there, transferred, accounted for. The helium nucleus formed in the core is slightly lighter than the 4 protons that made it, and that mass, that specific deficit, is the photon that just arrived. Not metaphorically, the mass that went missing in the core is the energy that warmed the hand. Same quantity, same total, converted through a series of forms across 100,000 years and 150 million kilometers. Conservation held the whole way. The sun has been spending its mass this way since before the Earth had oceans, since before anything lived anywhere on this planet. Every photon that has ever warmed any surface here, everyone that ever drove any act of photosynthesis, that ever evaporated any water, that later fell as rain, that ever warmed the shallow water where the first chemistry toward life began, every one of those was mass that became energy in a stellar core and found its way outward. The sun is not burning, it is slowly becoming light, and the light is going everywhere, in every direction, most of it into the cold of interstellar space where it will travel for billions of years without encountering anything, carrying its small cargo of converted mass, the accounting intact, the total unchanged. Some of it, though, a very small fraction, the fraction that happens to intersect a small rocky planet at a particular distance, arrives, becomes chemistry, becomes warmth, becomes eventually the metabolic energy of everything alive here, becomes in the longest accounting you. The next chapter asks what happens when the conversion isn't available anymore, when the energy exists but has nowhere useful to go, when the accounting is still perfect but the currency has become somehow unspendable. Energy is conserved. That has been the whole argument so far, from the candle to the paddle wheel to the sun, through the neutrino and the mass energy equivalence and Noether's theorem, and it remains true. Nothing in this chapter changes it. The total is always the same. The accounting is always exact. But there is something else happening, running alongside conservation, that conservation doesn't speak to. Something that is not about how much energy exists, but about what the energy can do. And the two things, how much exists and what it can do, are not the same question. This is the chapter about that second question. Start with something concrete. A cup of coffee sitting on a table, hot initially, 100 degrees or close to it, and the room around it is 20 degrees, and that difference, 80 degrees of temperature gradient between the cup and everything surrounding it, is a resource. Not metaphorically, physically. That temperature difference can do work. You could, in principle, run a small heat engine between the cup and the room, and the engine would produce mechanical output as long as the gradient existed. The difference between hot and cold is exploitable. It has, in a technical sense, economic value. Now wait an hour. The cup is room temperature. The coffee cooled, the room warmed by an amount too small to feel, and the gradient is gone. The energy hasn't gone anywhere. Every joule of heat that left the coffee is still in the room, in the air, in the table surface, in the walls. The total energy of the system is exactly the same as it was when the coffee was hot. Nothing was lost. But the engine won't run now. The temperature difference is gone. The energy that was concentrated in the cup has spread into the room, thinning out until it's distributed so evenly across so many molecules that no part of the system is meaningfully different from any other part. The energy exists. You cannot use it. This is what entropy measures. Not the energy. The degree to which the energy is spread out, flattened, lost the contrasts and gradients that made it available to cause further change. High entropy means the energy is evenly distributed. Low entropy means it's concentrated somewhere. And the second law of thermodynamics says that in an isolated system, entropy increases. The gradients flatten. The concentrations spread, the differences even out. Always in one direction, never the other, spontaneously. The second law is not a conservation law. This is the thing about it that I think generates the most confusion. Or at least it generated the most confusion for me for a long time, because it sounds like one. It sounds like a rule about what energy does, the way the first law is a rule about how much energy there is, but the second law is about direction. It doesn't say how much, it says which way things go toward more even. Always. Heat flows from hot to cold, not from cold to hot. Gas expands into a vacuum. It doesn't spontaneously compress. Ink dropped into water disperses. It doesn't undisperse. These are all the same phenomenon, the movement toward more evenly distributed energy, expressed in different physical systems. The directionality is the same in all of them. Energy spreads, gradients flatten. Why? At the statistical level, the answer is almost embarrassingly simple. There are vastly more ways for energy to be spread out than for it to be concentrated. A system evolving randomly, molecules moving and colliding and exchanging energy without any directing principle, will almost certainly move toward more even distributions because there are overwhelmingly more of those states available. The concentrated state, the hot coffee, is improbable not because something prevents it, but because the disordered states so vastly outnumber it. Entropy isn't a force, it's a head count. The historian of science who first works through the reception of the second law always seems to find the same thing, which is that people found it disturbing in a way they didn't find the first law disturbing. Conservation of energy was, if anything, reassuring. The total is preserved. Nothing disappears. The universe is a closed book whose entries always balance. The second law said something different. It said the book balances, yes, but the entries become less legible over time. The information concentrates into configurations of decreasing usefulness. The universe has a direction, not just change, but a preferred direction for change. And the direction is toward evenness, toward sameness, toward a state where nothing is different enough from anything else to cause further change. The 19th century scientists who worked this out, Clausius, Kelvin, Boltzmann, were not celebrated with the same warmth as the people who found conservation of energy. Boltzmann, specifically, spent years defending his statistical interpretation of entropy against serious opposition, and died in 1906 without seeing it fully accepted. The idea that the universe was running down in some sense, that every process was consuming the available order and returning it as disorder. This was not a comfortable finding. The room smells faintly of something left on too long. Not burning, not unpleasant, just the dry, warm smell of a lamp that has been on since before dark. And outside the window, the night is the specific temperature that isn't cold enough to matter, but isn't warm either. Just present. Just the ambient temperature of an autumn evening doing nothing in particular. That smell, that evening temperature, these are entropy. The lamp's electrical energy has become heat, has become the slightly elevated temperature of a room that is, right now, a fraction warmer than it would otherwise be. The gradient will last a few hours. By morning it will be gone. The energy will still exist, in the walls, in the air that moves out when a window is opened. But the lamp will have done its work, and the work will be finished, and the difference it made will have been absorbed into the large, patient indifference of thermal equilibrium. This is not the lamp being destroyed. It's the lamp's energy finding its level. Water finding its level is the soft image at the centre of this, and it is not a perfect image. It breaks down under pressure, but it does something useful here. Water flows downhill, until there is no more downhill. Energy flows from concentrated to dispersed until there is no more gradient. In both cases, the substance is conserved. The water doesn't disappear, the energy doesn't disappear. What disappears is the difference in height, the difference in temperature, the difference that made flow possible. When the water has found its level, it is still there, just flat, just even, just done. The universe is doing this on a cosmic scale, slowly, and has been since the beginning. The Big Bang produced a state of extraordinary low entropy, not because it was hot, but because the matter and energy were distributed in a specific way that allowed enormous structure to emerge. Stars formed because matter was uneven enough to clump under gravity. Planets formed around those stars. Chemistry happened on at least one of them. All of that structure, every galaxy, every star, every molecule of every living thing, exists because the universe started with an enormous reserve of low entropy, an enormous reserve of available difference, and has been slowly spending it ever since. We are a long way from spent. The sun has billions of years left. New stars are forming. The entropy gap, the difference between the universe's actual entropy and its theoretical maximum, is still vast enough that the universe's capacity for structure and change and complexity is nowhere near exhausted. But it is decreasing. The direction is fixed. I want to be careful about what that means, because I think it's easy to hear it as something it isn't. It isn't loss, not exactly. The energy is conserved, and that part stands. Always, the first law doesn't bend. What decreases is the usefulness of the distribution. The universe doesn't become less, it becomes more even. These are not the same thing, and I think conflating them produces a kind of unnecessary bleakness in popular accounts of thermodynamics. The universe running toward maximum entropy is not the universe running out. It's the universe becoming gradually too similar to itself to generate the contrast that complexity requires. Which is, well, it is what it is. The second law doesn't take anything back. It doesn't destroy energy. It doesn't undo conservation. It just describes a direction. Everything flows toward the same temperature. The coffee cup is cold. The room is slightly warmer. The difference is gone. The energy is still there. It's just that the difference, the gap, the gradient, the space between the hot thing and the cold thing that every process in the universe requires in order to happen, that particular shape of the energy is finished, used, converted from something usable into something merely present. The accounting remains exact. Every joule that left the cup is in the room. The first law has not been touched, but the second law has been satisfied. The entropy of the system increased. The available order that the hot coffee represented has been distributed into the room so thoroughly that none of it can be recovered without importing new low entropy from somewhere else, another hot thing, another gradient, another source of the concentrated energy that makes engines run and chemistry happen, and organisms stay organized for the brief time they do. Conservation is not the whole story, it's the foundation. The thing that makes the rest of the story possible by ensuring there is always something to work with, always something present, never a void. But the story itself, the one about what happens to the energy after it's conserved, where it goes and what it becomes and how long any particular configuration of it remains useful, that story has a direction. And the direction is not destruction. It just looks sometimes from a certain angle like it is. The universe right now is noisy. Not in the acoustic sense. Space carries no sound, there is no medium for pressure waves to move through in the vast dark between galaxies, but in the thermodynamic sense. noisy with difference, noisy with contrast, hot things and cold things separated by enormous distances, energy flowing between them along gradients that have been in place since the first stars lit up roughly 13.6 billion years ago. The universe is, at this moment in its history, extraordinarily active. Stars forming, burning, exploding, galaxies colliding slowly, their stars passing through each other like two clouds of smoke interpenetrating. The individual stars almost never actually striking, because the distances between them are so vast that a galaxy is mostly empty. Black holes accreting, neutron stars spinning, chemistry happening on at least one small rocky planet near an ordinary star in an ordinary galaxy, producing things that look at the sky and wonder what it is. This is the Stelliferous era. The age of stars has been going on for 13.8 billion years and will continue for roughly another 100 trillion. 100 trillion years is a number that has no useful human analogy. The age of the universe right now is about 13.8 billion, so we're talking about a future period roughly 7,000 times longer than everything that has happened so far. And through all of it, stars will form, burn and die, each one spending its hydrogen, converting mass to energy, sending light outward in every direction. The total energy is conserved through all of it. The light that leaves each star carries a specific accountable quantity of mass energy that was once hydrogen in a stellar core. The accounting continues, as it always does, exact and indifferent to the scale. Star formation will end, not soon, not in any time frame that threatens anything we'd recognize as the present. But the gas clouds that collapse into stars are a finite resource, and stars process that gas into heavier elements that don't participate in fusion the same way, and gradually, over timescales so long that the current age of the universe's rounding error, the raw material for new stars runs out. The last stars to form will be red dwarfs, small and cool and extraordinarily frugal with their fuel, burning for trillions of years before they exhaust themselves. The last red dwarf will go out, eventually, and it will go out quietly. Not an explosion, just a slow dimming, a gradual cooling, until what remains is a dark object, a black dwarf technically, though none exist yet because the universe isn't old enough, made of degenerate matter, carbon, and oxygen packed so densely that quantum mechanical pressure is all that holds it from collapsing further. Cold, dark, the remains of a star, and still carrying energy. All the energy it didn't radiate held in its mass, locked in the structure of the degenerate matter, going nowhere. The first law persisting in the cold. This is the degenerate era, the age of white dwarfs and neutron stars and black dwarfs slowly cooling toward the temperature of the surrounding space, the age of dim objects drifting in a universe that has stopped making new light. The background temperature of the universe, already about 2.7 degrees above absolute zero, a remnant of the Big Bang's initial heat diluted by 13.8 billion years of expansion, will continue falling as the universe expands. The objects in the degenerate era are cooling toward a target that is itself moving, the ambient temperature dropping, the gap between object and background narrowing over timescales that have no name. There is something in this era that is almost familiar. The stars are gone, but their remains are still there. Still material objects with mass and structure, still carrying the energy of their former burning in their arrangement of atoms, and something that is deeply unfamiliar, which is the darkness. Not night dark, the dark you're probably in right now, which is full of ambient light from screens and streetlights and the moon. Actual dark. The dark of a universe that has stopped making photons in significant quantities, where the background radiation has stretched to wavelengths so long they barely qualify as light. Where the electromagnetic spectrum has thinned out to almost nothing. Almost, not nothing, the energy is still there. The cold objects are still radiating very slightly at the temperature of whatever they are, sending photons of extraordinary low energy out into space. The accounting holds, the total has not changed. The degenerate era ends not with an event, but with a shift in what is doing the most work. Black holes become the dominant objects. Not because new ones are forming in great numbers, though some mergers and collapses will continue, but because everything else has faded. White dwarfs cool to invisibility. Neutron stars spin down. The universe's content is, increasingly, black holes and the diffuse remnants of everything else. The spent matter, the cold dust, the long-separated particles that used to be part of structures and are now just present, at very low density, in the dark. Black holes are, in a sense, the universe's most patient energy stores. They contain the mass energy of everything that fell into them. The stars and gas clouds and particles that crossed the event horizon and were compressed into the singularity or near it. And they hold it with extraordinary stability. A black hole doesn't burn. It doesn't undergo fusion. It just sits, warping space-time around it, containing what it contains, radiating nothing by the classical physics. But, and this is the correction that Hawking worked out in 1974, a result that emerged from applying quantum mechanics to the boundary of a black hole rather than from any classical treatment, which is why it took until 1974 to find it. Black holes do radiate, very slowly, at a rate so low that a stellar mass black hole would take roughly 10 to the power of 67 years to evaporate completely, and a supermassive black hole on the order of a galaxy's mass would take something like 10 to the power of 100 years. 10 to the power of 100 years. This number is called a googol. It was coined by a 9-year-old, which is the kind of biographical fact that sits oddly next to the scale of what it's describing. The universe's current age is approximately 10 to the 10th power years. A googol is 10 billion 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 times that. The black holes will be evaporating for periods so long relative to everything that has come before that calling them long is a failure of language, not an exaggeration, just an inadequate word for something that has no adequate word. Hawking radiation is not the black hole losing energy into nothing. The energy the black hole loses is carried away by real particles, photons and other particles produced at the event horizon through quantum processes, carrying mass energy away from the black hole at a rate that increases as the black hole shrinks, so that the very end, the last moments of a black hole's evaporation, when it has shrunk to subatomic scales, is an energetic burst, a small explosion of radiation from an object that has been patient for longer than the current universe has been alive. That final burst carries the energy, somewhere, into the space that surrounds the evaporating black hole, as radiation, as heat, as particles that will eventually reach thermal equilibrium with everything else. Conserved, the total unchanged. The last black hole evaporates. The smell of the room, something faintly dusty, the specific dry warmth of air that has been circulated through the same space for hours, and the quiet that exists right now outside the window are the last sensory facts before what comes next. Because what comes next is the dark era. After the last black hole evaporates, the universe contains, and this is where description starts to fail in interesting ways, diffuse particles, photons of extraordinary low energy, electrons and positrons so cold and so separated that interactions between them happen on timescales that make even the black hole era look brief. The universe is not empty technically. There is still matter. There is still radiation. There is still energy. exactly as much as there has always been. The first law intact, the total conserve, every joule accounted for. But the distribution of that energy has become, the word I keep reaching for is flat. Not flat in the geometric sense, flat in the thermodynamic sense. The temperature differences that drove every process, every star, every chemical reaction, every self-replicating molecule, every thought, those differences have dwindled to the point where they are effectively zero. The universe is approaching thermal equilibrium. Every region of space is approaching the same temperature, which is approaching asymptotically absolute zero. Approaching, not reaching. This is the detail that I find genuinely hard to hold. The heat death of the universe is not the universe reaching absolute zero. It is the universe reaching a state where all remaining temperature differences are too small to exploit. The energy is still there. The photons are still there. The diffuse particles are still there, moving, carrying their tiny kinetic energies, obeying the same laws they have always obeyed. The first law is still intact, as it has always been, as it will always be. The universe doesn't die, the universe settles. There is a difference, and the difference matters, and it is easy to miss in popular accounts that reach for the drama of ending, when what is actually happening is a process arriving at its natural conclusion. A ball rolling across a surface gradually loses kinetic energy to friction, and eventually it stops, but the energy hasn't vanished. The ball is at rest in the only sense that physics recognizes, which is the sense of having reached a local minimum, a configuration that requires no further change. The universe arriving at maximum entropy is the universe finding that minimum, except that minimum is the entirety of space at near absolute zero, populated by photons too weak to do chemistry and particles too cold to interact in any meaningful way. Still there, just finished. The total energy of the universe in the dark era is the same as the total energy of the universe right now, in this room, with you in it, with the faint warmth of whatever is near you, and the light, if there is any, and the specific unrepeatable arrangement of matter and energy that constitutes this particular moment. The universe, in the end, does not consume itself, it does not run out. It does not violate the law that every chapter of this has been circling. The energy that exists tonight, in the stars, in the warmth of bodies, in the chemical bonds of every molecule in every living thing, in the light traveling between galaxies right now at 300 million meters per second, that energy will be present at the heat death. Different form, unimaginably different, spread so thin across so vast a space that the word present starts to lose traction. But there, accounted for, the total unchanged, the conservation law that Joule chased through his brewery and no other derived from symmetry, and Einstein folded into mass. That law holds in the dark era as plainly and as completely as it holds right now, perhaps more visibly. When everything has settled, when all the noise of conversion has stilled and the gradients have flattened, and the last photon from the last evaporating black hole has travelled to wherever it will travel, the only thing left to say about the universe's energy is that it is conserved. There is nothing else left to say. There is only one chapter remaining, and it does not go forward in time. It comes back. The body at rest is a specific thing, not an abstraction, a specific arrangement of matter with a specific temperature, somewhere around 37 degrees at the core, slightly less at the surface, radiating heat outward at a rate that depends on what's covering it and how cold the surrounding air is. Mass somewhere between 50 and 100 kilograms for most people, composed of roughly 7 billion atoms, 7 followed by 27 zeros, the majority of which are hydrogen, then oxygen, then carbon, with smaller quantities of nitrogen, calcium, phosphorus, and a long tail of trace elements, some of which are present in quantities so small they barely register, and yet are necessary for the whole system to function. That system is running right now, quietly, automatically, without requiring any attention. The heart is doing what it does. The cells are doing what they do. The brain, at whatever level of consciousness you're currently at, drifting probably somewhere between awareness and sleep, is maintaining itself with the same metabolic stubbornness it maintains at full alertness, burning glucose, generating heat, doing the electrical work of being a brain, even when the brain's owner has largely let go of the day. All of this is energy. Specifically, chemical energy converted from food, converted from organisms that also converted it from something else, traced back eventually to sunlight. Solar energy becoming plant chemistry, becoming animal chemistry, becoming the specific metabolic state of a body lying still in the dark. The sun is in there, obviously. You already knew that. But the sun is not where the story starts. Hydrogen is the beginning of everything, more or less. The Big Bang produced hydrogen and helium and trace amounts of lithium and essentially nothing else. The periodic table's first 3 elements unevenly distributed across an expanding universe, slowly cooling from the initial plasma state into something that could form atoms, then clouds, then the first gravitational collapses that became the first stars. Those first stars were not like the sun, they were enormous, hundreds of times the sun's mass in some cases, and they burned hot and fast, consuming their hydrogen in millions of years rather than billions, and when they exhausted their fuel, they didn't simply cool down. They collapsed and exploded. Supernovae of a violence that, I want to say staggering, but that's not quite the right word. Staggering implies something that still fits in a human frame of reference, and a supernova does not. More like a violence so complete and so brief that the star's entire outer envelope is ejected into space at significant fractions of the speed of light, seeded with every element the star's core produced during its burning. And those stars made elements. Inside a star, fusion doesn't stop at helium. It continues in the right conditions up through the periodic table. Helium to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, silicon to sulfur, and eventually, at the end of the chain, iron. Iron is where stellar fusion stops, because iron is the most stable nucleus. The point at which fusing 2 nuclei together no longer releases energy but requires it. The star builds an iron core, and the iron core doesn't burn, and without burning there's no outward pressure to counter gravity, and the core collapses. This collapse and the explosion it triggers scatters everything the star built. Carbon, oxygen, nitrogen, silicon, sulfur elements the universe had no significant quantities of before the first stars died, thrown outward into the interstellar medium, mixing with the hydrogen and helium that was already there, enriching the gas clouds that would eventually collapse into the next generation of stars and planets, and on at least one planet, into the chemistry that became cells. The oxygen you're breathing was made in a stellar core, not this star, not the sun, which is not hot enough to fuse carbon into oxygen in significant quantities, but an earlier star, a previous generation, a star that lived and died before the sun existed. The carbon in your cells, in every organic molecule in your body, same origin, made in stellar cores, scattered in stellar deaths, gathered into the solar nebula that became this solar system, incorporated into the planet, incorporated eventually into you. Iron is the one that stops me every time. Your blood is red because of hemoglobin, and hemoglobin is red because of the iron atom at the centre of each heme group, and that iron, every iron atom in every red blood cell carrying oxygen through your body right now, was made in a supernova, not in the gradual fusion sequence of a star's normal burning. Iron at stellar scales is made in the extreme conditions of core collapse, in the last moments of a massive star's life, in temperatures and pressures that exist nowhere else in the universe except in those brief violent seconds. The iron in blood came from a star's death. This is not. I want to be careful here, because it's easy to reach for the poetic version of this fact, and in doing so, lose the actual fact. This is not metaphor. The iron is genuinely, physically traceable to nucleosynthesis in one or more supernovae that occurred before the Sun formed, 4.6 billion years ago. The atoms were here before Earth was. They were in the nebula. They became rock, became ocean chemistry, became biological molecules, became the specific protein that carries oxygen in your specific blood. No new iron was created. The iron that was made in dying stars is the iron that exists now in the crust and the oceans and the bodies of everything that incorporates it. Conservation of matter, and beneath it, conservation of the mass energy those atoms represent, running through billions of years of stellar and planetary and biological history. The hydrogen is older still. The hydrogen in your body, the majority of your atoms by count, is primordial, made in the Big Bang, not in stars, not in supernovae, not in any process that has happened since the first few minutes of the universe's existence. Approximately 13.8 billion years old, those hydrogen atoms, and they have been many things in that time. Part of the interstellar medium, part of gas clouds, part of stars probably at some point, incorporated into stellar material, possibly fused and re-released, possibly surviving intact through stellar passage. Part of water molecules for an enormous fraction of Earth's history, part of organic chemistry, part of every organism in your lineage, going back to the first cells. Now, part of you. The oldest things in your body are the hydrogen atoms. They were there at the beginning, or close enough to it that the difference is technical. They have been conserved, not as hydrogen necessarily, not always in this form, but as mass energy, as the quantity that the first law describes across the entire history of the universe. They are here tonight. The breath going out right now, the specific breath, if you're aware of it, the slow exhale that happens without your asking it to, carries carbon dioxide, which means it carries carbon atoms that were, until recently, in your cells, and before that in the food you ate, and before that in the organism the food came from, and before that in the atmospheric CO2 that organism used for photosynthesis, or in the organic matter it consumed, and the chain goes back, link by link, to the first carbon atoms scattered by the first supernovae into the cloud that became the sun and its planets. That breath is dispersing now, the carbon dioxide molecules mixing with the room's air, the carbon atoms beginning a new leg of their journey, absorbed eventually by plants or remaining in the atmosphere for years, or dissolving into water and becoming carbonate chemistry. They won't stay yours. They haven't always been yours. You borrowed them for a while, for the specific purpose of being you, and now they're going back into the circulation. The energy that moves them, metabolic energy, the chemical energy of ATP, ultimately solar energy, ultimately the mass energy of hydrogen that fused in the sun, that energy is conserved through every step of their journey. The carbon atoms change hands. The energy accounting continues. There is something in all of this that I find not comforting exactly. That's not quite the word. More like settling. The kind of feeling you get when something that seemed complicated turns out to be one thing seen from multiple angles. You're a specific arrangement of atoms that are very old and will continue existing in various arrangements. After this particular arrangement ends, the energy running through you is borrowed from a chain that goes back to stellar cores and further back to the Big Bang, and it will be passed forward into whatever comes after. The conservation law is the thread that runs through all of it, the reason the chain is unbroken, the reason there was anything to become you into the first place. This script, all 12 chapters of it, was made without a studio, without a production budget, on the kind of timeline that a self-funded project runs on, which is whenever there's time. If it's given you something, a way to fall asleep that feels a little less like switching off and a little more like settling into something large, and you want to help it continue, there's a Patreon in the description. Alison, Matthew M. and Brian Winter have been there from early on, and because of people like them this exists. Thank you genuinely to all of them and everyone else there. The body at rest is still warm, 37 degrees at the core, slightly less at the surface, radiating heat outward at whatever rate the blanket and the air allow. The hydrogen in it came from the Big Bang, the carbon from a dead star, the iron from a supernova so violent it scattered its core across light years of space, and some of what it scattered ended up eventually here. The energy running through it all, metabolic, chemical, electrical, thermal, is conserved, has always been conserved, will be conserved in whatever the atoms become next. You don't have to do anything with that. It's just what's happening. It was always happening, even before there was anyone here to notice it, and it will go on happening in the patient way the universe does everything. Without hurry, without loss, the total always exactly what it was. Breathe out.